Okay, welcome back to another marathon for A-level math students. Today the topic is complex numbers. Now remember that complex numbers is a very dense topic, so I would strongly recommend that you go back and watch the lecture videos first if you haven't watched them already, and then watch this marathon to get the most benefit out of it. What I'm going to do right now is solve a number of questions. Remember that complex numbers is rarely on its own. It's sometimes combined with polynomials, sometimes with vectors, sometimes with basic algebra, sometimes with algebra, sometimes with trigonometry, and you'll see a range of questions here. Okay, beginning with the first question. It says the complex number 1 plus root 2i is denoted by u. So 1 plus root 2i. I'm going to use a calculator for a lot of calculations. I will tell you when I'm skipping over some calculations that you need to show on the exam, but I'm skipping over here just to get these done quickly. The polynomial x power 4 plus x squared plus 2x plus 6 is denoted by p of x. Showing you're working clearly, verify that u is a root. So what I need to do is I need to plug it in instead of x, and show that it's a root, and write down a second root of the complex root of the equation. Now if I know already that it's a root, I know that the second complex root should be its conjugate, so 1 minus root 2i should be the right answer for the second complex root of the equation, and that's there. Now I'm going to show you how to prove. So I plug it in instead of x power 4 1 plus root 2i squared plus 2 1 plus root 2i plus 6. Okay, what I'm going to do is I don't know how to do power 4, so I break it up into two squares. Okay, squaring is simple. Use a square plus 2ab plus b square, and that should give you the right answer. 1 square plus 2 root 2i plus 2i squared. Root 2i squared is 2i squared, and that's an important conclusion that we will have from here. Just let me write that down. Now what I'm going to do is I'm going to first try to simplify this bracket that I have. It becomes 1 plus 2 root 2i minus 2. I squared becomes negative 1, so this becomes minus 2. So I get 2 root 2i minus 1. So can I say that these first two brackets that I've written here should each boil down to 2 root 2i minus 1, and I can use that conclusion to go through my calculations quickly to I. So let's quickly then multiply that. That's again become 2 root 2i minus 1 whole squared. So that's easy to do again. So this becomes 8i squared. I'm going to enter the next line now. 8i squared minus 4 root 2i plus 1 plus 2 root 2i minus 1 plus 2 plus 2 root 2i plus 6. If I scroll it up a little just so that you can see. So what do I get? I get minus 8 minus 4 root 2i plus 1, and minus 1 seem to be cancelling out. Let's just get rid of that. I get 4 root 2i and plus 8. So everything seems to be cancelling out. So I get 0. So I've proven to you that this is the root of the equation p of x equals to 0. And write down a second complex root. That's something that I've already done. Find the other two roots of the complex equation, this. So again, what you need to remember is your basics from polynomial. Polynomials, again, I'm going to write that down. X power 4 for part 2, x power 4 plus x squared plus 2x plus 6 equals to 0. Okay, and what I was trying to solve, what I was trying to find is the other two roots of the equation. So if I know that u equals to 1 plus root 1 1 plus root 2 I is a root, I can use that information in order to do a comparison. I'm going to say that the first root was 1 plus root 2 I and the other root was 1 minus root 2 I. The conjugate of that, remember that complex roots always occur in pairs if your original equation has real coefficients only. So I'm going to say x minus 1 minus root 2I and x minus 1 plus root 2I were the two roots, the two factors that I had. Apart from that, there's going to be another quadratic factor because I need to make an equation with degree 4. So I'm going to use that information now on the right hand side to expand first, and then I'm going to do a comparison for these. Now it's important to expand these first. This becomes x squared minus x minus plus x root 2I, and then minus x plus 1 minus root 2I, and then multiplying with root 2I, so root 2xi plus root 2I. I'm being very careful because you often end up making silly mistakes here. Minus 2I squared. Okay, I sort of have run out of space in this one, so I'm going to move that a little to the left and say that this is ax squared plus bx plus c. Let's quickly see what's happening inside the first bracket. It's a complicated bracket. So I think this is cancelling out. This is also cancelling out. So I have sort of a real equation here. X squared minus 2x plus 1 and minus 2 into minus 1. So ax squared plus bx plus c. So I get x squared minus 2x plus 3. Now I'll do my expansion and then do a comparison. I think that's simple. If you've already done polynomials, you should be good at that. Let's quickly expand. I'm going to multiply x squared by all the terms, so bx cubed plus cx squared, and then minus 2x to ax cubed minus 2bx squared minus 2cx plus 3ax squared plus 3bx plus 3c. Okay, doing a quick comparison, I have a power 4 term that I compare to the power 4 term, so a is equals to 1. Then I go on and compare the other term. I have an x squared term, I don't have a cubic term, so x squared term is this term in the middle. What I could, in order to quickly do this, is compare the last term first, so 3c equals to 6, and that should give me the middle term as well. Comparing the x squared term now, I get 1 x squared equals to c minus 2b plus 3a. So 1 equals to 2 minus 2b plus 3 times 1. So that gives me 5 and minus 4. So b is equals to 2. So I have the other factor now. The question was asking me for roots. So I'm going to say that I'm going to again sort of make some space here and tell you what the roots are. I think I want to have enough space here. Okay, let's write that factor down. So a is 1, so that becomes x squared, b is 2, so that becomes 2x, and c is also 2. And the previous factor that I had was x squared minus 2x plus 3. Both are equals to 0. That one I already know. Let's try to solve this one first. Of course, I can't factorize this, so again I have to use the quadratic formula, minus b plus minus root of b squared minus 4ac over 2a. So now I'm going to use my calculator to simplify this quickly rather than spending time on this. I hope everybody knows how to simplify this, and you should also know how to do this on your calculator in order to check your answers. So I get minus 1 plus I and minus 1 minus I. So quite a time consuming question, so you get 10 marks out of this. So you have about 15 minutes to do this. Okay, moving on to the next question. Question number 2 says the complex number z is given by z equals to 4 minus 3i, 1 minus 2i. Express z in the form x plus iy, where x and y are real numbers. So the only thing that I need to do is I need to rationalize this number, and you must have done it in the lecture, that you multiply with the complex conjugate of the denominator. You multiply both the numerator and the denominator in order to rationalize this. In the denominator you get 1 squared minus 2i squared, and in the numerator you get 4 plus 8i minus 3i minus 6i squared. Simplifying that quickly, again I could have done this entire thing on a calculator, but since this is the first time that I'm doing this in the marathon, I've done it in detail. So that gives me 10 plus 5i divided by 5, because I squared is negative 1, so 4i squared becomes plus 4, minus 4i squared becomes plus 4i plus 4, and I get 5 in the denominator. So the ultimate answer is 2 plus I, and I think that's the right answer. So find the modulus in argument. When you want to find the modulus, that's relatively simple. The modulus of z is simply the x and the y squared inside a root and added together, so root of 5. When you are doing the argument of z, you first need to know what quadrant z lies in. So the real and imaginary are both positive, so it lies in the first quadrant. Then I need to use tan inverse of y over x or tan inverse of b over a, whatever you've learned it, whichever way you've learned it. Let's quickly do that. Again, your calculators are capable of calculating modulus and arguments on their own. You could use your calculator to do that. Remember that this should come out ideally in radians. It can also be in degrees, it won't matter right now, but for later questions it would. So I'm just going to write it in radians right away. 0.464. Since it's in the first quadrant, the answer is directly the angle that comes up, so it's alpha. Then that was part 2. Part B says find two square roots of the complex numbers 5 minus 12i, giving you an answer in the form x plus yi. Now this is a tough question. Hopefully you've done that in the lecture as well. I'm going to try to do that. What I'm asking you is the two complex roots. So what I'm asking you is 5 minus 12i inside a root, and I want you to express it in the form x plus yi. Now these questions are always done with comparison, so what you do is you square both sides and then you try to do a comparison, the real parts with the real parts and the imaginary parts with the imaginary parts. So I get 5 minus 12i equals to x squared plus 2xyi plus y squared I squared y squared y squared. So I get x squared plus I squared y squared plus 2xyi, which is x squared minus y squared plus 2xyi. So I need to now compare the real part with the real part. So I'm going to say that 5 should equal x squared minus y squared. And minus 12 should equal 2xy. So if I take a substitution, what I get is y equals to minus 12 over 2x, which is minus 6 over x. So I'm going to use that in the other equation that I have and try to solve that. X squared minus 36 over x squared equals to 5. Pick a common denominator. This becomes what we learn in AS math. This has become a disguised quadratic equation. So if I solve this quadratic equation, 36. I can actually factorize it by just breaking the middle term. I can see the factors 9 and 4. So x squared, I could also do this with a calculator. So I'm getting x squared minus 9 and x squared plus 4 equals to 0. So x squared minus 9 equals to 0. X is therefore plus and minus 3. x squared equals to minus 4. Now I don't want to go on and calculate x squared minus 4 because it says where x and y are real numbers, so this becomes non-real, therefore it's discarded. I just need to consider the real ones, 3 and minus 3. When x is 3, y should be minus 6 over 3, which is minus 2, and here minus 6 over minus 3, which should be 2. So the two complex roots are 3 minus 2i and minus 3 plus 2i are the two square roots. Let's check if our answers are correct. Yes, that's correct answer. Moving on to question number 3, it says throughout this question the use of a calculator is not permitted. To be honest, you can use a calculator to do some calculations. It's not that you can't even touch a calculator, and I would strongly recommend that you check your answers or whatever the case may be. The idea is that you cannot put equations on a calculator and sort of get to the final answer without doing any working. So make sure that you do an appropriate amount of working on such questions. Plus, this is an older question. The newer questions don't rarely have this line written at the start. The complex numbers w and z satisfy the relationship this. Given that z equals to 1 plus I, find w, giving your answer in the form x plus yi, where x and y are real. Okay, so I have to find w. I just need to replace z with 1 plus I. That's simple. 1 plus 2i, I plus I squared plus 2. Okay, that becomes I minus 1 plus 2. So what I want to do is I also want to write it like that, 1 plus I. So w is 1 plus I. What I need to do again is I cannot accept an I in the denominator, so I need to rationalize that, and by rationalizing I have to multiply both the numerator and denominator by the conjugate of the denominator. So I get 1 minus I plus 2I minus 2I squared, and 1 squared minus I squared. 1 plus I minus 2 times minus 1. 1 minus minus 1. So I get 3 plus I divided by 2. That gives me 3 over 2 plus 1 over 2i. Is that the correct answer? Yes, that's the correct answer. So fairly simple. Let's look at part 2. That's the more challenging part. Part 2 says, given that instead that w equals to z and the real part of z is negative, find z, giving your answer in the form x minus yi. So what's happening here is that w equals to z and the real part of z is so in this case I need to find z and not w. That's something that you should notice right at the start. So what I'm going to do is replace w with z, because that's what the question is saying. If I cross multiply this, I get iz squared plus 2z equals to z plus I. iz squared plus 2z minus z minus I equals to 0. So what I have is a quadratic equation in z. Can I say that a is I, b is 1, and c is minus I? You see, the question expects you to do the entire quadratic formula manually rather than putting it on a calculator. So you have to do that, minus b plus minus root of b squared minus 4ac over 2a minus 1 plus minus 1 plus 4i squared over 2i minus 1 plus minus, that becomes 1 minus 4 gives me minus 3, so that's 2i. Now minus 1 plus minus root 3i over 2i. Again, this needs to be rationalized, so what I'm going to do is I'm going to multiply both the numerator and the denominator by simply just I. When you don't have two terms in the denominator, the only thing that you have to do is remove I from the denominator, and I can be removed simply by making it I squared. In order to make it I squared, you just simply multiply it with another I. It wouldn't make a difference if you multiplied it with 2I or minus 2I, it would still give you the same answer at the end. So plus minus root 3 I squared over 2I squared. So I'm left with minus 1 plus minus. Okay, now I need to separate these positives and negatives because it's getting more complicated. Okay, so minus 1 minus root 3 over minus 2 and minus I plus root 3 over minus 2. Let's say something here. And the real part of z is negative, so I need to find which real part of z is negative. So I need to separate them into their real and imaginary parts. So this gets separated into this, and this gets separated. So in this case, the real part of z is positive, so that's not the correct answer then. So discarded. That should be the correct answer. That becomes I over 2 minus root 3 over 2. So that is my correct answer, and I should make a box over it. Yeah, it's just written in a different order, and I should write the correct order because it says x plus y, so my order is incorrect. Okay, hopefully everybody understood that. It's again an 8-mark question. It should have taken me about 12 minutes to solve. I think that's what I took. Let's see question number 4. It says the complex number z is defined by z equals to 9 root 3 plus 9i over root 3 minus I. Find, showing all you're working an expression for z in the form r e iota theta, where r is greater than 0 and theta is between minus pi and pi. R is basically the modulus, theta is the argument. You must have studied this in the exponential form of the complex number that you've done before. Okay, so I will first have to rationalize this. I don't think I can do it without that. So multiplying it with root 3 plus I, root 3 plus I. So I get 3 minus I squared. Multiplying the numerator gives me 9 into 3, 27 plus 9 root 3i plus 9 root 3i plus 9i squared. 27 plus 18 root 3i minus 9 over 4. Okay, I'm just going to check my answer so that I don't do the next part incorrectly. I can't possibly check it without a calculator right now. I put the calculator in complex mode first. So 9 root 3 plus 9i over root 3 minus I. Yeah, I am correct. So 9 root 3 over 2i. Okay, so I have z in the right form. Now I can quickly calculate r and ei theta. R is basically just the square added together and a root put over it. So I'm just going to put that quickly on a calculator and get my answer. Okay, I am getting this r as 9. Okay, and I just found out that the calculator can do all of this quickly. I just pressed option and it gave me options to convert this into that form. Okay, in any case, In order to calculate the argument, I will first have to find out the real and imaginary parts. The real and imaginary parts are both in the first quadrant, so the argument of z should simply be tan inverse of 9 root 3 over 2 divided by 9 over 2, and 9 and 9 cancel, 2 and 2. So tan inverse of root 3 is just pi over 3. That's got 60 degrees. So I get z in my desired form. Z is therefore 9e 1 over 3 pi I. Then it says the two square roots of z giving you an answer in the form are ei theta. Now I could do a long solution for this in the way that I just did the previous question. I could take this form basically and sort of put it equals to x plus yi. I'm going to get two numbers out of it, and then I could go on and calculate the modulus and arguments of those again and get to my final answer. But what I can also do is I can do something here to get this answer, and I could say to get it directly in the form r iota theta. So what I know from my calculations is that z can be expressed in this form. So what I have done is written it inside a square root. Now we all know that when you take a root of 9, it's either plus 3 or minus 3. Now if I want to write this, can I write this as root of 9 and e power 1 over 3 pi power half. So that gives me pi over e, that gives me plus minus 3 e pi over 6i. Now I want you to notice carefully what I do here. I first written this, okay, but what the question says is, okay, this one is fine because r is greater than 0 and theta is between minus pi and pi. That's fine, that's one square root is fine. But this other root has a problem. It has r as minus 3. Now when we talk about polar coordinates, what we simply mean is that this would simply mean that if this 3e I over pi over 6i was in this quadrant, what minus 3 would simply mean is that it was in the opposite direction. So minus 3 was here. So if I want to write this as 3, what I need to do is I need to change the argument on this one. So what I'm going to do is I'm going to say that again this angle was pi over 6, so this one angle is also pi over 6, but when arguments are measured in this quadrant, this is the second negative quadrant, they are measured clockwise and as negative angles. So this argument would basically be pi minus pi plus pi over 6i. So if I want to turn this 3 into a positive number, I'm going to say that's 3, and then I'm going to say that it's pi over 6i. And that should be my final answer. 5 pi over 6, my bad, minus 5 pi over 6i, and that should be my final answer. This happened because I changed 3 into minus 3 into positive 3, and in order to compensate that I had to change the argument that was there. Slightly more challenging. You could do a longer way out and sort of find out x and y coordinates, but that's too long a solution and I wouldn't recommend doing that. Okay, let's look at another question. This is the polynomial this. Now this is a slightly longer question. It has a very long last part. Let's quickly try to get through the earlier ones so that we can quickly reach the last one. It says where m is a constant, it is given that z plus 2 is a factor of p of z. Find the value of m. I think that's relatively simple. If you put in z as minus 2, that should give you the answer. That's basic polynomials, minus 2 cubed plus m minus 2 squared plus 24 minus 2 plus 32 equals to 0. So I get minus 8 plus 4m plus minus 48. Let's quickly do those calculations. Minus 4m equals to 12. 12. 24 and 6. So that's relatively easy. Part 2, hence showing all your working, find the three roots of the equation probability of z, not probability, p of z, function of z is equals to 0. So I'm going to just use my ideas from polynomials just like I did in the previous question. This is basically a comparison question, so I'm going to do that. I'm going to say that this becomes 6z plus 24z plus 32, and one of the factors is z plus 2, and the other is going to be az squared plus bz plus c. I find a little odd myself to be writing z instead of x, but that's what the question says, so I'm just going to do that. Quickly expanding this gives me az cubed plus bz squared plus cz plus 2az squared plus 2bz plus 2c plus yeah, that's it. I have a bit of a crisis writing z and 2 differently. Let's just do that. So a is 1, 6 should equal b plus 2a, b is 4, and 32 equals to 2c, so c is 16. I should verify that. Yeah, that's 16, that's correct. So z plus 2 and z squared plus 4z plus 16, so either that equals to 0 or this equals to 0, so z squared plus 4z plus 16 equals to 0. What I'm going to do is, I know I need to use the quadratic formula minus b plus minus b squared minus 4ac. Just to speed up calculations right now, what I'm going to do is I'm going to put this on a calculator and see if I get the right answers. 1, 4 and 16. Okay, I'm getting minus 2 plus 2 root 3i and minus 2 root 3i. You would have gotten the same answers had you used the quadratic formula. I'm just trying to speed up the calculations here a little, not a lot. Part 2b. Part 2b is a long question. See, it's 6 marks, so you need to be careful. Now it says the 6 roots of the equation p of z squared. So what I need to first do is I need to first make sure that I know what I'm trying to solve. Okay, the thing that I'm trying to solve is that z squared replaced with this in this entire equation. So this actually becomes z power 6 and then mz powered 4 and 24z and 32. Now that wouldn't help me because I don't know how to solve a question or an equation that has power 6 involved. What I can still say is that all the answers that were valid for z are now valid for z squared because the equation has sort of remained the same. So whatever answers you got for z are now answers for z squared. So the three answers that you got here were these. So z squared is equals to minus 2. That was the first root. So I'm going to say that z squared equals to minus 2, or z squared equals to minus 2 plus 2 root 3i and minus 2 root 3i is also z squared. I have a bit of a space crisis here, but let's just try to do this. Okay, so Then if I'm trying to find 6 roots, that means each of these will give me 2 roots each. So I'm going to say that just putting a root there and root there should simply give me root 2i with a plus and minus. So that's 2 roots. You see that here. Now with these, now I just learned how to calculate the square roots of a complex number. They cannot be done in a straightforward way. Again, I need to use comparison. So what I'm going to replace this with, instead of using x and y right now, what I'm saying is I'm using a plus bi. So whatever the complex root of z will be, it's going to turn up in the form a plus bi. So I just write that there. I am still using the first set of answers from here. I haven't used the other set. I will have to use that other set. This is a 6-mark question. It's a long question. It's probably going to give me sort of advantage, some advantage when I try to solve it, solve the second part. But right now, I'm using the first one only. So a squared plus b squared 2abi plus b squared I squared equals to minus 2 plus 2 root 3i. So a squared minus b squared plus 2abi equals to minus 2 plus 2 root 3i. Now again, a comparison is necessary. So a square minus b square equals to minus 2 and 2ab equals to 2 root 3. 2 cancels and b is basically root 3 over a. So root 3 over a squared equals to minus 2. A squared minus 3 over a squared equals to minus 2. A power 4 minus 3 equals to minus 2a squared. A power 4 plus 2a squared minus 3 equals to 0. Again, this is a disguised quadratic equation. I can factorize it simply by saying that this is 3a squared minus a squared minus 3. A squared plus 3 plus 1 minus 1. A squared plus 3 equals to 0. So a squared plus 3 and a squared minus 1 equals to 0. Again, this gives me a as a non-real number, so ignore it. You use this one. A squared equals to 1. A is therefore equals to plus minus 1. When a is plus minus 1, b should be either plus minus root of 3 depending on the sign. So I found another set of roots. One of my answers was 1 plus minus root 2i. Another set that I found is 1 plus root 3i, a and b, 1 plus root 3i, and minus 1 minus root 3i. So I have another set of coordinates that I found. I think that's this one. Now for the third set of coordinates, again I need to use this and do the same process again. So I'm assuming this process will be a little easier based on something that I've already done, but I want to be absolutely sure. So I'm going to go on and take a root, replace this with a plus bi again, minus 2 root 3i squared a squared plus 2abi plus b squared I squared minus 2 root 3i. That was inside a root, so the roots cancel out. So a squared minus b squared plus 2abi. So a squared minus b squared is again equal to minus 2, but in this case 2abi is now equals to minus root 3i, minus 2 root 3i. So the 2's, no, let's just do a comparison. So 2ab is equals to minus 2 root 3. The 2's cancel out and b is now equals to minus root 3 over a. So it's sort of the same solution, but the only difference that I have is that So I can just say that this is again going to boil down to a is equals to plus minus 1, 1 and minus 1. But in this case, b would, if a is minus 1, that's minus root 3, and this one should be plus root 3. So the two other complex roots are therefore 1 minus root 3i and minus 1 plus root 3i. I think all of these 6 are different. There are 2 here, 2 here, and 2 here. And that is your final answer. This is a good 6-mark question, which was why it also took me a long time to solve. A total of 13 marks, which means you have about 18 minutes on the exam to solve this one. That's the first part of the marathon. We'll be back